Hi, my name is Dave Lynch. I'm going to present about isomorphisms and graphs. Um, Isomorphisms, when you think about them very informally, are actually a pretty easy idea. My daughter and I played with these little magnets that connect in different ways, and we were talking about my class and isomorphisms, and basically we were trying to go, hey, are these two structures the same? Which is one way to look at it, or a slightly more formal is there an edge preserving matching of the vertices? She didn't really understand that. She's only 7. But she was able to look at these two graphs, G and H here, and figure out very quickly that they are not equivalent because basically H is missing an edge and to connect them. You could also, a little bit more formally, we could go, hey, this is a tree, this is not a tree, this has a cycle of 3, this does not, therefore they are not the same. However, we could change these just slightly to say, hey, yeah, they are isomorphic. And I'm going to do that right now. I'm going to redefine H in such a way that it does create an isomorphism. So now I've redefined H. It's a new graph. And yeah, they are definitely isomorphic because each vertice is represented over there. And their structure is the same. They both have this triangle or cycle 3, and then they both have this one part that sticks off of it, if you will. So they are isomorphic. The structure is the same, and that's that. So to say that these two functions are the same, or to write it a little bit more formally, is we would say that G is isomorphic with H. The reason why we do not say that they are equal is because maybe in G these are representative of numbers, whereas in H, for some reason, these are labels of people, and we'll call them Bob, Jane, Harry, and Fred. And so they're not exactly equal, but they certainly have the same shape, therefore they are isomorphic. Okay, let's move on. So in order to prove that two graphs are isomorphic, what we need to be able to do is create some sort of function that maps each vertex in one of the graphs, to a vertex in the other, and these vertexes must be linked in the same way. And so there's two new words that we need to talk about. One is injective and the other is surjective. We're going to start with talking about an injective function. So we're trying to create this function phi right here. This is the function phi. And what we're trying to do is map our letters A, B, C, and D from this graph to our numbers over here in this purple graph. And I think that you're probably looking at this going, but hey, Dave, these two graphs, they're not isomorphic because they got this one part sticking off there and this one doesn't have it, so they're clearly not isomorphic. And you'd be correct. These are not isomorphic. But I just want to talk about these words first, just so we get a little bit better of a idea what's going on, what we're trying to do. So we're going to start mapping our vertices in G to our vertices in H, and we can kind of do this pretty quickly here. We can look at this and go, hey, A sure does look like 1. A sure does look like 3, right? These are similar. If you were thinking, well, couldn't we map it to 4 or 5? You're right, you could have. But we're just going to do the more obvious one. So A goes to 3. D goes with 4, so we'll put that there. C would have to go with 5. And then B obviously has to go with 2. That's the thing that's linking all of these vertices together, that 2 in the middle there. And so we could look at this and go, hey, this is an injective function because we have created a mapping of distinct vertices in G to H. However, for us to create a bijective function, which we'll talk about momentarily, this needs to be surjective. And surjective means that each element, I'm going to write this out, each element, or I should say vertex, must be mapped to, and you can see that 1 is clearly not mapped to, so this particular graph H is not surjective. I'm sorry, this function phi is not surjective because H, this 1 in H has not been mapped to. So what I'd like to do, although this isn't how you do it, how you prove something is isomorphic, but I'd like to just show you the differences, is I'm going to edit H. We'll call it H prime just to be a little bit more consistent. We're going to have this new graph H prime, and I am going to erase this. Whoops. I'll put that back in. I'm going to erase that. And once I've erased that, we should be able to look at this pretty easily and go, hey, G is isomorphic with H prime, which is great. And what I'd like to point out is when a function, this function proves that they're isomorphic, but when a function is both injective and surjective, that combination, the combination of injective and surjective, is a new word, bijective. So the function needs to be bijective in order to prove that we have an isomorphism, and it also needs to preserve the edges or the links between the vertices. Okay. So I would like to look at a couple different graphs here, and these graphs, our goal is to figure out which of these graphs is isomorphic with each other. And one of the nice things about finding isomorphisms is that it's relatively easy to throw out an isomorphism. And we can do that just looking at some of the really basic fundamentals of their structure. Let's first talk about the vertices, the number of vertices. If we look at this graph in the top left, we can quickly see that there are 5 vertices in that graph. If we look at this one over here, we can say that there are 6 vertices in that one. So instantly, we should be able to realize that we cannot create a bijective function that would link these two graphs together because one has 5 elements, one has 5 vertices, and the other has 6. So it's not a one-to-one relationship. But let's continue. We can look down here and go, well, this one has a vertex of our 5 vertices, and this one over here also has 5 vertices. So we can quickly go, well, this one is not going to be an isomorphism of the rest. But for the sake of practice and explanation, we are going to continue on as though we don't realize that yet. So we could count the number of edges as well. And in this particular graph, we have 1, 2, 3, 4, 5 edges. In this graph, we have quite a few more edges. Each one of these has degree 3, so 3 times 3 is 9. That has 9 edges. This graph over here has 1, 2, 3, 4 edges. And this graph over here has 5 edges. So if we were to look at this, again, we could quickly throw out this bottom left one because it doesn't have the right number of edges. So really, the only 2 graphs that could be isomorphic to each other would be these 2. But again, we are going to pause with that idea and just continue on. Another thing that could throw out options is the degree sequence. So if we do the degree sequence of this one, we can look at each one of these vertices and notice that they all are degree 2, so we could say it's degree 2 normal, or we could just list them off to the degree sequence as 2, 2, 2, 2, 2. We can go over here and do the degree sequence of this, and we can look at this and say, oh, those are degree 3 normal. So it's going to be 6 3s. And then we can look down here and we can see that there are some different degrees. We have a degree 1, 2, 2, 2, and 1. So our degree sequence in here is 2, 2, 2, 1, 1. I don't need that comma, but that's all right. We'll do that. And then we look at this bottom right one and the degree sequence, they're all 2s, 4, 5. So with just the degree sequence, we can see that again, this and this cannot be isomorphic with anything because the degree sequences are different. So that could be another way we check. And the last way that I'd like to point out to see if it's worth looking for this function phi, that is our big goal, right? To prove that something's isomorphic, we need to create the function phi. That links the vertices together. Last thing we could look at is other things that we happen to notice. Like, very quickly, this bottom left one, I see that it's a tree. None of the other graphs are trees, so I could kind of throw that one out. I see that this one here is a cycle 5. I look up here and I can tell that this is a bipartite graph. Whoops, I misspelled bipartite graph. And then if I actually look at this tree again, I can see that that's bipartite as well. And now I'm kind of wondering, well, this one, this star, has to be cycle 5 for these to be isomorphic. And it actually is cycle 5, right? We can go 1, 2, 3, 4, 5, and we can see that it is cycle 5. So there's a really good possibility that these two graphs are isomorphic. So our last job to actually prove it is to find our function phi and label it appropriately. So I am about to do that. I need to just give myself a little bit more room. I'm going to get rid of this graph, this tree over here, because we know that's not isomorphic to these other two. And give me a second. There we go. So we need to create a function phi that maps this graph to this graph. So I'm just going to start labeling 1, 2, 3, 4, 5. And this graph down here looks pretty darn symmetric, so it probably doesn't matter where I start, but just for ease, I'm going to start with A. So I'm going to try mapping 1 with A. Okay, so that's fine. And then I'm going to look and go, number 2 does not touch number 1. So that means whatever I map with 2 can't touch A. So I can't choose B or E. And D and C look pretty symmetric. It would turn out that it would work out either way, but just because I want to, I'm going to choose D. So now I'm going to look for 3, and I'll notice that 3 has an edge with 1, but doesn't have an edge with 2. So I need something that has an edge with A that doesn't have an edge with D. So what has an edge with A and not D? Well, that can't be E, it can't be C, but B has an edge with A, but not D. So B must be linked to 3. And then I got to look at 4. 4 has edges with 1 and 2. So whatever I choose over here has to have an edge with A and D. So A and D, well, that leaves us with E for that one. And then lastly, 5, well, it needs to go with whatever letter we have left, which is C, but 5 has an edge with 2 and 3. So C had better have an edge with D and B, 2 and 3. So D and B, yep, are linked with C. So now, because we've created this function and we know that it is bijective because every element up here was preserved with an element down there and vice versa, and we know that our edges have been preserved, we can say that they are isomorphic. And I'm just going to call this G and call this H so that we can see how you would write that. We would say G is isomorphic with H. And if it's isomorphic with H, then the converse must be true, right? We can write it the other way. So there you have it. Let's take a quick look at the very formal definition. We're going to come back to this. So for two graphs, G and H, to be isomorphic, there has to be a bijective function, phi, such that all the vertices in G are mapped to a vertex in H, such that the edges are preserved. If they're linked in our graph G, after you do the function and what they've been mapped to must be preserved in H as well. If this is true, then these graphs G and H are isomorphic. I'd like to just do one more example problem. This is actually the problem from homework 5, problem 3 that we did for class. When I approached this problem, I looked at it at first and said, no, they can't be isomorphic. Turned out I was wrong. But let's just go through the same logic that I went through when I solved this. I first looked at the number of vertices, and I went, oh, the number of vertices is 8. Each graph has 8 vertices, and you can check that yourself. And then I said, well, how many edges does each graph have? And after some careful counting, I discovered that each graph has 16 edges. Okay, so then after I did that, I looked for the degree sequence, and I noticed that both graphs had degree sequences of all 4s because each element, each vertice has degree 4. So this is 4 normal. They're both 4 normal. And then I looked and I went, this one here is bipartite. It's just kind of set up in that way, and it's actually a complete bipartite because each element in the top group is linked to an element in the bottom group. And I'm just going to color it just to show that it is bipartite. And so then it got me wondering, like, maybe this one over here isn't bipartite. But when I colored this, I realized if I look at just the vertical ones, they do not connect each other. No vertical ones are connected, but they are connected to all the horizontal ones and vice versa. So oddly enough, both these graphs are bipartite. Bipartite. Oh my goodness. Bipartite. Sorry about that. And so then all I needed now to do was to create the function phi. And one thing that was pretty easy was the fact that these are both complete complete bipartite graphs with 8 vertices. So what we're going to do is, in order to create this graph, we need to create labels. I'm going to label this one A, B, C, and D, and E, F, G, and H. And I'm going to label this one 1, 2, 3, 4, 5, 6, 7, and 8. So now I just need to create this link, and luckily enough, because they're complete graphs, there's lots and lots of ways you can do this. I'm sorry, complete bipartite graphs. There's lots of ways we can do this, but I'm going to do what seems to be the most obvious. I will list A, B, C, D, E, F, and G, and H, Pardon this, I'll move that 5. Whoops. I'll move the 5 over here just to get it out of the way. And so I listed all my vertices in this graph on the left, and I just need to match them up. And because in this graph on the left, A, B, C, and D are in blue, and these are in red, I'm just going to keep that consistent. So, although I wouldn't actually have to. So I'm going to label this A goes with 5, B 6, 7, and 8, and then 1, 2, 3, and 4. And we can kind of check this. I'm not going to go through every element, but like if we look at element 2, 2 is linked to 5, 6, 7, and 8, which means that F had better be linked with A, B, C, and D, and F is here, and it is linked with A, B, C, and D, and that can be what's it called? That you can check for yourself for that. As I started this out, I was talking about my daughter for a little bit, and she and I did some of this stuff together, and she has gotten into stop motion. Whoops, that is not the right button. She has gotten into stop motion movies, and she thought it would be fun to do one with me. So this is my first attempt at a stop motion video. I would just like for you to check it out. Think about it as a bit of a review. About halfway through the video, there is an interesting, the isomorphism happens up here, and you actually get to see how those structures are the same. So here it is, the video. I'm going to hit play, make it bigger. Whoops, let's make it bigger. Shoot. That is not good. Oh well, let's just show it like that. All right. Well, so it is isomorphic. I apologize. I will let you do it. See it again. So are they isomorphic? And then here comes the movement of those vertices. Anyway, thank you very much for your time. I appreciate it, and have a good day.